In the last module, we talked about particle in a one-dimensional box, two-dimensional box, and three-dimensional box. In the one-dimensional box, what we did was a box which was extending from 0 to A, and what we have taken as potential energy inside the box is 0 and potential energy outside the box is infinity. Okay, if you remember. Okay. Now what I am going to tell you is a box where one of the boundaries, potential energy outside one of the boundaries is finite, not infinite. So this box we are going to talk about, where on the left hand side you have potential energy V is equal to infinity. On the right hand side you have potential energy V is equal to V. So the boundary height is less. Okay. And then in the region 1, inside the box, the potential energy is equal to 0. Okay. So a slight departure from the particle in a one-dimensional box, which we have done. So what we have here is that on the left hand side, the particle cannot be there because the potential energy is infinity, but particle could be in region 1 or in region 2. So in both these regions, we will find out the wave functions of the particle and we will see what is the result. So in region 1, again you can write the same as you did in the previous module for particle in a one-dimensional box or infinite potential well, which you say we can write the Schrodinger wave equation, and again you can write 8 pi square m divided by h square E is equal to k, and then it is very similar to the previous one because here also the potential energy is 0, and there also in particle in a one-dimensional box also potential energy was 0 in region 1. So you can have a solution like a sin kx plus b cos kx, which we did in the earlier also, and in terms of exponential function we can write a prime exponential plus ikx plus b prime exponential minus ikx as the solution of this Schrodinger wave equation. Okay, so psi 1 is for the region 1 and wave function we can write. What happens in region 2? In region 2 we cannot say this v is equal to 0 because this v has the value equal to v. This potential energy in region 2 is equal to v. So what you can do is you will write this equation, and then there could be two cases. One is that the particle energy is less than the V, potential energy outside the boundary, or particle energy could be higher than the V value or the potential energy outside the boundary. So we will first talk about a particle having energy less than the potential energy outside the boundary. And in that case, if you write k square as 8 pi square m by h square v minus e, then you can write this equation d square psi 2 divided by dx square minus k2 square also you can do. If you want, you can write k2 square and k2 square. So psi 2 is equal to 0. And then the solution will be c exponential kx plus d exponential minus kx. Okay. And the solution you can check in the same way as you did it for particle in a one-dimensional box. You can differentiate this psi 2 once and then twice, and you will get the same equation back, from which you started. Okay. So this is just checking the solution of this psi 2. And what does this psi 2 tells you? This is not a imaginary number. This is not an imaginary function. It's a real function. Okay. So it cannot be converted into sine and cosine, and it's not a periodic function. Okay. So this psi 2 does not report a periodic motion and has no wavelength associated with it. Okay. For the region 2, when E is less than V. Okay. Now, if you apply the boundary condition, what was your case? Problem was this one. At x is equal to 0 and at x is equal to A. So this was V is equal to 0, this was V is equal to V, this is V is equal to infinity. So at x0, psi 1 should be 0 because it is region 1 and region 2 wave function is in region 2. So psi 1 should be 0. And if you put this value, what was your solution? Solution was a sin kx plus b cos kx. Okay. So this has to be equal to 0. So sin 0 will be 0 and then b has to be equal to 0. And if b is equal to 0, then the solution remains is a1 a sin kx. The same thing which we did in particle in a one-dimensional box in the earlier module. Okay. So this is the solution of region 1. And applying the boundary condition that x is equal to 0 is equal to psi 1 0. Now, if you go for psi 2, then this is the wave function. And what does it mean? This function becomes infinite at x is equal to infinity. So what do? This c into exponential kx becomes infinite. So in order to make the functional acceptable, you put c is equal to 0 and then psi 2 becomes equal to d exponential minus kx. Okay. So the wave function for the region 2 now is restricted to d exponential minus kx. Okay. Now we go for the second boundary condition, and second boundary condition is that x is equal to a. And what will happen at x is equal to a? At x is equal to a, both psi 1 and psi 2 should have the same value. Okay. And also the slope of the wave function should be same for psi 1 and psi 2. So the second boundary condition is psi 1 is equal to psi 2 and d psi 1 by dx is equal to d psi 2 by dx. Now you have the psi 1 value and you have the psi 2 value. Psi 1 value is a sin kx and psi 2 value is d exponential minus kx. So if you put these values, you can write a sin k1x plus d exponential minus k2x. Okay. And if you differentiate these functions, then what do you get? You get a k1 cos k1x minus k2 d exponential minus k2x. Now this part d exponential minus k2x is actually equal to a sin k1x. So what you can write? A k1 cos k1x is equal to minus k2 a sin k1x. And if you rearrange this equation, what do you get? Minus k1 by k2 becomes equal to tan k1x. It's very easy. Now the ratio of k1 and k2 is equal to tan k1x. And what does it mean? K1 and k2, if you put the values, k1 was 8 pi square me by h square and k2 was 8 pi square m v minus e divided by h square. So it will be 1 by k2 and you get this root under e divided by v minus e. Okay. So k1 by k2 if you get, then you can write tan k1x is tan k1 value is 8 pi square me by h square raised to the power 1 by 2 into a. Okay, because at a we are talking about, so what you can do is at a x is equal to a, so you can put this is equal to a or all x will be equal to a, that you can put, and then you get this equation. Instead of x you have a and minus k1 divided by k2 is equal to minus e raised to the power half v minus a raised to the power half. Okay, so this also you can write tan k1, because at x is equal to a we are talking about, so you can write a. Okay, now you have this equation tan k1x is equal at x is equal to a becomes equal to tan 8 pi square me by h square raised to the power half a is equal to this one. Okay, now this equation must be satisfied, and what does this equation tells you? That in this equation mass is known. Okay, a is known, size of the box is known, v is known, potential energy outside the box is known. The only thing which is unknown is E. And for this equation to be applicable, we say that only certain values of E will be possible, but there will be no quantum number. In contrast to the earlier particle in a one-dimensional box, in this case, when you have a finite boundary condition, and for a case where the particle energy is less than V, what we say that the energy is quantized without having any quantum number. So this is the variation which we are getting, and we have the equation like this one. So if you plot the LHS and RHS of the equation, you get a plot like this one. So only at these intersection point where the LHS and RHS becomes equal, the equation is satisfied. This equation is satisfied only at these 3 points. Okay, point 1 in this diagram, this qualitative diagram, at point 1, 2 and 3, the equation is satisfied. So only these E values is possible, rest all values are not possible. So energy is quantized, but we don't have a quantum number here. In contrast to what we did in particle in a one-dimensional box, two-dimensional box or three-dimensional box, everywhere quantization was along with a quantum number. Now in this case, we don't have a quantization. We do have a quantization without having a quantum number. Okay, so this is the case where when you have the E value, then you can determine the A and D, and this equation you can write for A divided by D, and a ratio can be determined from this equation. Okay, so in contrast to particle in a one-dimensional box where potential energy V is equal to 0, what you get is energy equal to n square h square divided by 8 ma square, and there the energy is dependent on the value of n, that is quantum number. In contrast to that, if you have one of the boundary as a finite potential across the boundary, across one of the boundary, if you have finite potential, then you don't have a quantum number, the quantization is there. Okay, and this will be the shape of the curve, because at this point you see, at this particular point where x is equal to a, at this point x is equal to a, and at this point you will have psi 1 here and psi 2 here, so both psi 1 and psi 2 will be equal. This was the first boundary condition, and the slope also should be continuous. So d psi 1 by d psi 2 is equal, d psi 1 by dx is equal to d psi 2 by dx. This was the boundary condition. While at x is equal to 0, you do not have psi 2, you have psi 1 only, so psi 1 was equal to 0. Okay, so these two boundary conditions. So what you observe is that when you plot a wave function, the plot of the wave function goes beyond the boundary. What happens if this is the case when particle energy is less than the potential energy V across the potential barrier? What happens if you have a particle energy higher than the potential the energy across the potential barrier? Now particle has higher energy, so it can cross easily the pathway, the boundary. Okay, so now you have the same psi 1 a sin k1x and psi 2 c sin k2x plus d cos k2x you can write, or in the exponential form you can write these equations, no issue, as we did earlier. The only thing which you have to consider is that energy is greater than potential energy, so rest of the thing will remain same. K1, K2 will also remain same. Now here we say that psi 2 consists of sine and cosine term. Okay, psi 2 consists of sine and cosine terms, so it will oscillate without being infinite. Okay, but it is not zero even at x is equal to infinity. So you see, it is not zero even at x is equal to infinity. So one of the condition which you get is, so for fixed value of constant c and d, the wave do not change in the amplitude, and there are fewer boundary conditions. Means particle energy is higher, so boundary is not able to restrict the particle within the boundary. It will go beyond the boundary, and if it will go beyond the boundary, then there will be no quantization also. Okay, so quantization itself is lost. Therefore, psi cannot be normalized, nor is E quantized. Okay, so the energy value is not quantized in this case when energy of the particle is greater than the potential energy across the boundary. Okay, so finite potential energy barrier leads to two different cases, one in which energy is less than the potential energy, and another case in which E is greater than potential energy. In case of E less than V, you have quantization. In case E is greater than V, you don't have the quantization. And even in the case of E less than V, you have quantization, but you don't have a quantum number. Okay, so these are the differences from the particle in a one-dimensional box, which we did in the earlier module. Okay, so this you should remember, and this is utilized in many different problems. Okay. Now another thing which I will do here is that if you have a potential barrier and particle is moving from region 1 to region 3, what will happen? Okay, so if in this case we suppose that particle energy is less than the V. This is the potential energy barrier in region 2. Okay, this is the potential energy barrier with thickness 0 to A. So it's not a box, it's a potential energy barrier. Now what will happen if a particle comes in the region 1, whether it will be able to cross region 2 and go to the region 3 or not, this we are going to talk about. And if particle goes from region 1 to region 3, crossing this potential energy barrier, this is called tunneling. Okay, so what again, for this we have three different regions, region 1, region 2, region 3. For all these three regions, we can write the Schrodinger wave equation, and what we have taken here, in region 1 and region 2, the potential energy is equal to 0. V is equal to 0 here also, V is equal to 0 here also. So region 1 and 3 is very similar, and particle energy is less than the potential energy barrier, V. So this E is less than V. This E is less than V. And then we have to see whether the particle is able to cross this second region and go to the third region or not. Okay. So If you write the Schrodinger wave equation in the similar way as in the particle in a one-dimensional box, you can write a sin k1x plus b cos k1x. Okay, or in the exponential form, you can write as a exponential I k1x plus b exponential minus I k1x for x less than 0. Okay, so on the left hand side. On the extreme right hand side in region 3, also you can write the similar equation with psi 3 value, and psi 3 also will be same. Okay. Now, the constant I have changed, f sin k3x plus g cos k3x, or in the exponential form you can write. So, both k1 and k3 are same in this case. Okay. The region, first region and the third region are similar. Potential energy is 0 here also, potential energy is 0 here also. Okay. And k1 and k3 becomes equal. What will happen to a region 2? Okay. Now, one thing, before going to the region 3, if you look at this equation, okay, what does this indicates? That g exponential I minus I k3x, it tells you that the wave is moving on the left hand side and there is no force to let it move in the reverse direction. So we say g becomes equal to 0 and then psi 3 becomes equal to f exponential I k3x. Okay, this we can do. What does these exponential terms indicates? And if you look at region 2, what you can write is this equation, d square psi 2 dx square 8 pi square m e minus v. Now v is not equal to 0. So again it will be minus k2 square, and the solution will be in the real form, not in the imaginary form. Psi 2 is equal to, this we did earlier also, c exponential k2x plus d exponential minus k2x for the potential barrier region 0 to a, for x 0 to a. Okay. So what we have is that for the two regions, psi 1, psi 2 and psi 3, all three regions we have the wave functions. For psi 1 region, we have a exponential I k1x plus b exponential minus I k1x. For psi 2 region, you have c exponential k2x plus d exponential minus k2x. And for psi 3 region, you have f is equal to e exponential k3x, g exponential minus I k3x. If you look at the physical significance of these 1, 2, 3, 4, 5 and 6 exponential terms, it is like this one. So, a exponential I k1x tells you about the incident wave moving in the right direction. Then it is b exponential minus I k1x, it's going in the minus x direction, so it is a reflected wave towards the left. Okay. Say similarly, c exponential k2x is a barrier wave moving to the right, and then d exponential minus k2x is barrier wave moving to the left. F exponential I k3x tells you that the wave has been transmitted, it has crossed the potential energy barrier and it has gone on the right hand side. So it's going in the right hand side, F exponential I k3x. Then G exponential minus I k3x is the incident wave moving in the left direction. Again, in the third region, it's moving in the left direction. Okay, that I said it will become equal to 0, G becomes equal to 0. Okay, so what we are interested in is this part, A exponential I k1x, which is the incident wave moving in the right direction, and F exponential I k3x is the transmitter wave moving in the right on the third region. So this tells you the incident light, this tells you the transmitted light which has been transmitted. So how much of light has been transmitted can be obtained, or how much of the particle, because of its wave nature, is crossing this energy barrier, it will be given by these two terms only, F and A. Okay, and a ratio of 2 is called transmittance or transmission probability. So transmission probability is actually F star F divided by A star A, and this we have to find out, that whether it is probable that the particle crosses the potential energy barrier because of its wave nature or not. Okay, this we are going to find out. Okay, so boundary condition, if you apply at x is equal to 0, psi 1 is equal to psi 2, again you can write, and so the in order to make the slope also equal, d psi 1 by dx equal to d psi 2 by dx. So exponential terms, A exponential I k1x plus b exponential minus I k1x is equal to c exponential k2x plus d exponential minus k2x. Okay, and what does it tell you? It tells you that A plus b is equal to c plus d, that you can write. Okay, now for this one, for the differential terms, if you differentiate, what you get is this one, and I k1 a minus b plus k is equal to k2 c minus d. Okay, and then you have a minus b I k2 I square k1 c minus d, and I square will be minus 1, so it will be d minus c, and a minus b I k2 divided by d minus c. So what you have is this term a plus b is equal to c plus d, and then you have a minus b is equal to k2 by k1 I have taken z d minus c. So these two terms we get from the first boundary condition, x is equal to 0 is equal to psi 1 is equal to psi 2. If you go beyond that and second boundary condition at x is equal to a, you remember the problem was this one. You have a potential barrier from 0 to a. This was region 1, this was region 2, this was region 3. So at x is equal to 0 we did psi 1 is equal to psi 2, and x is equal to a, what we will do, psi 2 is equal to psi 3. And so the slope also equals, so d psi 2 by dx is equal to d psi 3 by dx. Okay, the concept involved is same everywhere. Okay. Now what you can write for psi 2, you write psi exponential k2a plus d exponential minus k2a is equal to f exponential I k3a, where I am not writing g because I said g will be equal to 0. Okay. So f we can write, and if you rearrange this equation, then keep the d term on the left hand side and bring the c term on the right hand side. It's the only change, and then you have d is equal to f exponential I k3a plus k2x minus c is equal to exponential 2k2a. Okay, so this you get d. What about the differential terms? So differential terms you write, and if you differentiate this equation with respect to x, what you get is this one, and same rearrangement will give you a d is equal to this one. So you have a d value from the differential term and you have a d value from psi 2 is equal to psi 3. You can equate both these terms, and if you equate both these terms, what you get is this one. F is equal to exponential I k3a plus k2a minus c exponential 2k2a. So this you get from here, and this you get from here, c exponential 2k2a minus I k3 by k2 f exponential I k3a plus k2a. Okay. And now you rearrange this one. Okay, f term on the left hand side, c term on the right hand side, and then further f term on the left hand side. So take a exponential I k3a plus exponential plus k2a. Here also you have exponential I k3a plus k2a. So take this exponential term common. Then you have f plus f I k3 divided by k2 is equal to 2c. This is the same 2c exponential 2k2a. Okay. Now this you can write as this 2k2a I have written as exponential k2a, and exponential k2a I can write, and then exponential k3a again you can write like this one. Okay. So what do you get? One of this exponential term will go, and then you can write exponential I k3a into f also we have taken outside. So 1 plus I k3 by k2 plus 2c exponential k2a, and this k3 by k2 term I can write as 1 by z, and so it will f by divided by 2 1 plus I divided by z exponential I k3a minus k2a. Okay, so this term we can write. This k3a I have brought on the right hand side. This exponential comes on the right hand side. Okay, and it goes to the denominator, and then it becomes minus a k3a. Okay, minus becomes plus. Okay, so this is the same thing. K3 by k2 will be equal to 1 by z. So that is already there in the previous slide also. Okay. Now similarly, what you can get is d is equal to f divided by 2 1 minus I divided by z exponential I k3a plus k2a. So c we have determined, and see in the similar fashion you can determine the d also. And if you determine d, then if you look at this equation, what do you get? You get, if you add this, b and b will go, and you have 2a c plus d plus iz d minus c, and slight rearrangement will give you 2a is equal to c 1 minus iz plus d is equal to 1 plus iz. Okay. If we say now if c is equal to 0 for the sake of simplification, okay, what does it happens? It gives you an equation 2a is equal to d 1 plus iz, and d is already known to you. So d is this one and 1 plus iz. If you rearrange this one, no rearrangement except this 2 is coming on this side, f divided by 4, 1 minus iz minus 1, 1 plus iz minus 1, and then exponential I k3a plus k2a. Okay. So now we say that if you want to find out this one, a square, mod a square and mod f square, it will be, so you will square this equation, and if you square this one, it will be mod f square divided by 16. 1 minus iz minus 1 will be 1 plus iz minus 1. So both are imaginary quantities. So 1 plus iz will become 1 minus iz. And then you have exponential I k3a. Then again it will be plus, and the next term will be minus exponential minus I k3a. Now this is e raised to the power k2a. You don't have I here. So it will be exponential 2k2a. Okay. And finally, what you get is the ratio of mod of f square divided by mod of a square, and this comes out to be 16 exponential minus 2 k2a. So this k2 term remains here, and the size of the box, the width of the potential energy barrier is also there. Okay. And I said you that this ratio is the transmission probability, and this we have determined mod of f square divided by mod of a square. Okay. So the transmission probability will mainly depend on the thickness as well as the k2 value. And what is this k2? K2 is actually minus 2 divided by a. Actually, exponential minus 2 k2a we can write as exponential minus 2 divided by h cross 2m v naught minus e raised to the power half. Okay, where v naught is the potential height of the potential energy barrier, m is the mass of the particle, and a is the width of the potential energy barrier. So these are the three factors on which the tunneling of a particle will depend across a potential energy barrier. Okay. Now, what we say that z is essentially a constant, so the denominator is a constant, and your tunneling is less. Now what happens? If you look at this equation, the tunneling will be proportional to what? The term exponential decay in terms of a. So what will happen? Higher the energy barrier, tunneling is less. So v minus e, if very high, chi will be smaller. Okay. Then mass, lighter particle will tunnel more easily. Okay. Heavier particle will not tunnel through. Okay. So transmission coefficient depends on the width of the energy barrier, height of the energy barrier, and mass of the particle. Okay. Higher the energy barrier, less will be the tunneling. Larger the particle, massive the particle, less will be the tunneling. Okay. And then height of the barrier, width of the energy barrier. Higher the energy width of the energy barrier, then also the tunneling will be low. Okay. So low mass, width of a small width of the energy barrier, and lower height of the energy barrier will facilitate tunneling through this energy barrier. Okay. And this is observed in many different cases in chemistry, and many different phenomena can be explained. Say for example, alpha particle comes out of a radioactive nuclei. Okay. Then you have the radioactive nucleus, it's positively charged, alpha particle is positively charged, and then it is coming out of that massive nucleus. So this can be explained based on the wave nature of the particle or tunneling from the this tunneling results that because of this tunneling effect, alpha particle can cross the energy barrier and can come out of the radioactive nucleus. There are many others, but we are talking about the theory. So the theory of tunneling is this one. Okay. Next, we will talk about other problems which is there, and we will apply Schrodinger wave equation to another system which is called simple harmonic oscillator. Thank you.